Today I will discuss the last part of activated complex theory, or it is called the transition state theory, and I have already derived the final formula of activated complex theory, and I had also given a problem to you that what are the physical significance of entropy of activation, enthalpy of activation, and free energy of the activations. Of course, standard free energy of activations. So that is the actual meaning of the transition state theory or activated complex theory. As we know that the general formula of activated complex theory is K. As you all know that all the theories of the reaction rate started with the rate constant is equal to Boltzmann constant, absolute temperature, that is the general formula of transition state theory proposed by Henry Eyring. And we have derived this formula with the help of statistical thermodynamics. We used vibrational partition function as well as the translational partition function, and ultimately we got this thing. And the second part of this activated complex theory is that the thermodynamic formulations. And it is all, you know that there is a very common formula, delta G is equal to minus RT natural log of K. As because we are dealing with the activated complex, so everything here we are considering the transition state. So sometimes we can write like that also. So if I substitute the value of delta G, the K, so finally we will get exponential minus delta G. You can write like that by RT. This is the final formula of transition state theory. Now, as because the delta G is related to delta H minus T delta S, so we can write final formula K. I have already discussed these things, but application part is important. And if I substitute the value of delta G here, so I will get exponential minus delta H divided by RT, and exponential, because here is also minus, so it is plus, positive, this T cancel, R. So in sometimes this equation is called Winey-Jones and Eyring equation. Winey-Jones and Eyring equations. Now we'll see that what is the application of this transition state theory. Now the first application is transition state theory is that with the help of this transition state theory, one can determine three important thermodynamic parameters. First application, thermodynamic parameters. If time permits, I will give you some numerical problem. Thermodynamic parameters. What is the importance of these thermodynamic parameters? I will explain gradually that with the help of these thermodynamic parameters, basically three. One is free energy of activation, standard free energy of enthalpy of activation, and free energy of the activation. With the help of these values, we can figure out the reaction mechanism. We can figure out the reaction mechanism. Reaction mechanism. Say for example, suppose you are getting some negative values. Delta E is equal to suppose minus 50 kilojoule per mole. I am just giving one example. Suppose you are getting negative value of entropy of activation, standard entropy of activation, or suppose you are getting some positive value, plus 25 kilojoule. So on the basis of these values, you can figure out the reaction mechanism. So now I will explain that suppose all the reactions are not unimolecular, some reactions are also bimolecular or termolecular reactions. Some reactions takes place in the solution phase, some reactions takes place in the gaseous phase. So there are two equations. One is for unimolecular type of the reactions, another is for bimolecular type of the reactions. Suppose you are performing some unimolecular reactions, then the transition state theory will be slightly different. And if you are using or if you are doing some bimolecular reactions, then the transition state theory will be slightly different. Slightly different. Okay. Now I will explain the application for unimolecular reactions and for bimolecular reaction as well as for the gaseous reactions. Okay. So let me start. It is very simple, very simple, and then I will also explain that how that day also I discussed, but most of the students were absent that day. That is very important, that is called the Eyring equation, that how do you determine graphically the value of delta S and delta H. I told that day also. That is actually called Eyring plot. That means if now I am talking about the Eyring plot, very important. Eyring plot is important. Graphical representation of delta S and delta H. Now if what I am doing, Eyring plot. So if I take the logarithm, so natural log of K, I can write like that. Natural log of KBT H, it's like that, minus delta H RT plus delta S standard you can write like that. In some books it is like that, so there is no harm. My meaning is this standard entropy of activation. That's all. Or if I rearrange this equation, how do I rearrange this equation? If I rearrange this equation, natural log, right, like K is the rate constant, H, KB, you know, Boltzmann constant, 1.38 into 10 to the power minus 60, minus delta H RT plus R. What I am doing? I am doing the iron plot for determination of delta S and delta H graphically, one of the applications. So if I plot a graph between natural log of K and H, KB and T, and 1 by T. Suppose this is -1, -2, -3, like that, temperature, whatever it is. So I will get a such type of plot. Suppose 3 temperature, 1, 2, 3, 4. So you all know this y is equal to x equal to c. This part is gradient is m. So slope is equal to minus and intercept I'll give some numerical problem so that you can understand very easily. And if you convert it to natural log, to log base 10, so you know that it is delta is divided by 2.303 RT, like that, or delta is 2.303 RT. So this is a graphical method by which you can determine enthalpy of activation as well as the entropy of activation, but for that you have to perform at least 4 experiments at different temperature, and you will get 4 rate constant values. Then these are constant, Planck constant you know value, Boltzmann constant you know the value in one temperature, so you can determine the. So this is one of the application of this transition state theory is the iron plot. Okay. Now I will discuss that what should be the formula of transition state theory for unimolecular reaction and then for bimolecular reaction. So because it is a very big chapter, now you can understand there are 2 parts. First part is the statistical formulation of transition state theory. Again in statistical formulation there are 2 parts. One is using vibrational partition function. You determine the final equation. Another is translational partition function. So that is one part of the transition state theory. If some examiner asks derive the transition state theory, so you will derive up to this. And this part today I am discussing with you, that is the second part of the transition state theory. Or sometimes if examiner asks write the application of transition state theory, then you have to write this part. And sometimes there is a possibility of numerical problem. After this class, I will give some of the numerical problems for the homework. So if you are able to solve all those problems, then it will be good for you. Okay. Now the last part, application, last part. Okay. So, first, taking logarithm. So if I, so it is, here I can write natural log of k, rate constant, natural log of kb, Boltzmann constant, minus natural log of Planck constant, plus natural log of t, plus natural log of k. Because we are dealing with the activated part, so you can write like that. So, if I take the derivative, differentiation with respect to temperature, so d by dt is equal natural log of k is a constant, difference is also a constant, and you all know that d by dt with respect to temperature T, it is 1 by T, and it is d by dt natural log of capital K. So what should I write here? d by dt of natural log of k from here 1 by t plus d by dt of natural log of. Okay, so I am getting this formula. Now before I derive further, as I told you many times, that all these theories are interrelated. All these theories are interrelated. That means Arrhenius equation is the most important point, and we all know that, again I should mention the Arrhenius equation. I must use the Van 't Hoff, all are interrelated, Van 't Hoff hypothesis. What is Arrhenius equation? We know that dy, sorry, again small mistake, K is equal to EA. Now it is energy of activation, isn't it? So again we need the formula of the Arrhenius equation. Then you must know that Van 't Hoff related to delta E standard, it is internal energy. Internal energy. In some books it is written also du also, so no problem. But it is inter equally, right? Sorry. RT square, I think. So here we can write EA divided by RT square d by dt of Arrhenius equation, k by RT square is equal to 1 by T in place of RT square, internal energy. So if I solve it, so it is RT square, you know, RT plus delta E is equal to EA by RT square. So what I am getting? I am getting what I am getting. Now the problem start in red color. I am getting EA is equal to RT plus internal energy. Standard you can write like that, whatever it is. But when I apply the transition state theory, my formula is K is equal to KBT H exponential minus delta H R. But here I am getting E. Here it is delta H. So how I replace that delta H? Because when you perform any experiment in T1, T2 and T3 and T4, suppose you are doing the hydrolysis of, again I am using this most simplest example, hydrolysis of methyl acetate at 4 temperature. So you will get energy of activation, that means EA. But in our main equation there is a term delta H. So I have to replace this delta H with the EA. So should I proceed? I can. I can also now remove this part also, because now we are getting only 3 things important: this main formula and this main formula. And you might have, if I just make you clear that if I just write it is normal cases, you know this is actually reactant, this is suppose transition state, and always there is a, you know, that is 0 point energy. It is also zero point energy of reactant, and it is 0 point energy of active state, and also there is the state. And here is also the total amount of energy. Of complexes. So basically you know that this is actually, you consider this, suppose this is normal energy state to this state, you call it is the energy of activation normally. But we should consider the difference between the 0 point energy of the reactants and the 0 point energy of the this is actually, this part is important, this part, critical energy we can call it. And here is also some energy of the reacting molecules, and we can calculate then this energy. this energy. Now this is actually difference between delta E and delta E and etc. like that. I will explain all these things. So it is not like that the delta H or delta E is exactly same. Maybe for unimolecular reaction, delta H equal to delta E. But for bimolecular reactions, I cannot say that both are equal. There must be some difference. So let me just solve this part. How we solve this part? Why? Because our main equation is delta H. Here we are getting this thing. So as we know that EA, very simple, RT plus delta E. Actually, I have to replace this delta H. That is our main objective. So we know that, again some thermodynamics, enthalpy is equal to H is equal to E plus PV. You know these things. And because here there is a change in all these thermodynamic parameters while coming from reactants to activated complex. Everywhere we are interested to measure that difference. So I can write that is the delta H. We write delta E plus P delta V plus V. These are all undergraduate level. We are doing for constant pressure, that can be eliminated. So delta H is equal to delta E equal to P. Why we are doing all such type of things? Because in normal cases we are getting E is equal to RT delta E. Our main equation there is a delta H, so I have to replace that delta H. So therefore I am doing all these things. Now I told you that there are two applications. One is for unimolecular reaction. So two applications, unimolecular reactions, another is the bimolecular reactions. I am not showing any example, gaseous reactions. I am not showing any example. So if it is, now every time we are considering the transition state. So therefore, standard we always write like that. Standard is always equal. It is up to you. So you know that suppose bimolecular reaction A plus B is equal to X and then product. So number of moles change. We can, you know that PV is equal to RT in RT. So P delta V is equal to delta N RT. So it is a unimolecular type of the reactions. So there is no change in, because A is converted into A. Suppose number of moles of activated complex is 1 minus 1. So 0. So there is no question of delta V. So as I told you, when you see that big graph in second semester, when you will study the RR-Kane theory, Rice, Ramsperger, Kallol and Marcus theory, which is the modified form of transition state theory, you will understand the actual meaning of this delta E and delta H and critical energy. Because here For unimolecular reaction, there is no difference between delta H and delta E. So I can write like that: EA again. I am now doing the unimolecular reaction, not bimolecular reaction. So EA is equal to RT plus, in place of delta E, should I write delta H? Because for unimolecular reaction, delta H and delta E is equal to same, so you can write. So delta H standard is equal to EA minus RT. You follow my point or not? Again, I am doing for unimolecular reactions where there is no change in volume, 1 to 1, 0. So no. So here delta E and delta H is equal to same. Delta H is exactly equal to delta E. So I have just substituted this value. So finally, I have to write the formula for unimolecular reactions. What I will do, when you in homework, when you solve numerical problems, one for unimolecular reaction, one for bimolecular reaction, you can see the clear-cut difference between the values. And as many times I told you that there is a very good book, Physical Chemistry Through Problems, Dogra and Dogra. There are a large number of numerical problems are given in that book, so you can see the difference. Or even you can see the Atkins, and I am using this derivation from the book of Chemical Kinetics by K.J. Ledler. So you can refer this book for complete understanding. So what now I am doing? I am writing the final formula of transition state theory for unimolecular reactions. So this is K, KBT, H, same. Now in place of delta H minus, here what I will write? EA minus RT divided by RT exponential R. So you follow my point? So this RT, EA by RT. So what I can write like right here. So in place of delta H, it is and exponential RT divided by RT. So you can write simply exponential, value is no meaning. So what is the final formula? This K observed rate constant is equal to KBT Boltzmann constant, absolute temperature, Planck constant, exponential EA RT E delta S by RT. Now what is the difference between main formula and this formula? Now you will be happy because with the help of simple thermostat and simple you can calculate the energy of activation. So you can substitute the value of energy of activation here. I will explain the why we are modifying this equation. Is it okay? Now I am doing for bimolecular reactions, bimolecular gaseous reactions. This is the last part. Now for bimolecular reactions, from here you can change these things for bimolecular reactions. Now for bimolecular reaction, you know, AB X product, single entity actually, this single entity, or you can write also A plus B, no problem, whatever it is, transition state. So total number of molecules change, delta N. Number of moles of the product minus number of moles of the reactant. Here number of moles of product means transition state. So it is 1, minus 1 and 2. So the value is minus 1. First point, the difference between unimolecular and bimolecular reaction. So here you can, if I write like that, delta H standard is equal to delta E standard P. I write like that, PV is equal to nRT. So P delta V is equal to delta nRT. So here I can write delta nRT for bimolecular. So again, delta H standard is equal to delta E. Because delta N is equal to minus 1, so it is minus RT. So what I am getting? Very simple, but you have to do some practice. Otherwise, it is very simple. Delta H is equal to delta E standard minus RT. Why it is minus RT? Because value of delta N for bimolecular reaction is minus 1, so it is minus 1. So now I have to substitute the value of delta H, or we can use here also. Delta H is equal to delta N by RT. What is our main formula? This is EA divided by RT. This is our main formula. So delta E is equal to delta H standard plus RT. So you can EA is equal to RT plus RT. Why 2RT? Because already there is RT, that is RT, so 2RT. So delta H is equal to EA minus 2RT. Just you follow this point. Again, you just, if you have any doubt, just you go through all these things. First, for unimolecular case is different, bimolecular gaseous reaction is different. So delta H is equal to EA minus 2RT. So what now I will do? I will substitute the value of delta H in our main equation. This is for unimolecular. Now I am doing for bimolecular. So last. Everything I can remove now except this part. Everything you can do. So what now I am doing? I am doing this is there. So now I am doing the last formula for bimolecular reaction. So K, the numerical question may ask from this side, K, KBT, H in place of delta H. So what should I write? Exponential minus EA minus 2 RT, isn't it? Divided by RT. And then again exponential delta S R. So again what I'll do? EA by RT, 2 RT by RT. So final formula, K is equal to KB T H, red color, exponential minus EA by RT. This, the minus minus plus, exponential 2 RT divided by RT. So exponential power 2. Then, so what is the difference between, as I told you, there is a very small difference, and you know, if you are a mathematics student, you can understand what should be the value of this exponential or 2. 1.7 like that, very small value. So now you compare these two values. One for unimolecular, this part is same, KBTH, this part is same. Exponential E by RT, this part is same. Exponential, only thing is that there is a one additional term, ES. You can write in front also, no problem. That means you can write like that. Now my last part, that what is the relationship between the transition state theory and collision theory, as well as relationship between the transition state theory and Arrhenius equation, and how with the help of any formula you can determine the value of delta S. So last part. These are all very simple. Only thing is that you have to read some good books like Atkins, Levine, Ledler, and derive it step by step, because there are 3 derivations. So step by step you derive it. So what now I am doing? I am determining one simple formula for delta x, and that will be my homework problem. So if I take the logarithm, so natural log of, you see here, KB T H, no problem. Natural log of K is equal to this, minus, because I am taking log, EA by RT plus, I am doing for unimolecular, not for bimolecular, R. Just think over it. Remember your old days, school days. If I slightly rearrange this equation, that is natural log of K plus EA RT, anybody, natural log of KBTH plus delta S R. What is this? Anybody? Just I am giving 1 minute. All are interrelated, as I told you. All these equations are interrelated. Anybody? Class, in the class? Are? हाँ बताओ, anybody? Yes, no, Arnia's theory, but what should I write here? You are right, it is Arnia's theory, but what should I write here? Anybody? No. So natural log of k is equal to natural log of a minus a by rt. So natural log of k plus a by rt is equal to frequency factor. What? This is Arnia's equation. Taking logarithm, log of k is equal to log of a minus e by rt. Log of k, if I just substitute log of k plus e by rt is equal to, so it is natural log of a. Frequency factor is equal to natural log of kBT h plus delta s and r. So why I am doing all these things? Because I have to determine the delta s value. So very simple. So what I will do? So I will give some numerical problem, then you will understand. A minus natural log kBTH is equal to delta S R. So delta S is equal to R, whatever the value. So these are interrelated. So now let me summarize the whole thing. Today I have discussed the thermodynamic formulation of transition state theory, or you can call it the application of transition state theory. I have determined the most important. If you are a kineticist and you are doing chemical kinetic research, suppose there is an unknown reaction, you are unable to predict whether it is a unimolecular reaction or bimolecular reaction. So what you will do, you will perform some of the experiment at different temperatures, and on the very basis of these formula you will determine either graphically by the iron plot or by simple method, because frequency factor you have to determine with the help of the temperature. So you will get this value of the delta S, then delta G and delta H, and on the basis of the magnitude of these thermodynamic parameters you can figure out the reaction mechanism. It is a thumb rule I have already given. Has anybody solved my question? Saturday I had given some physical significance. Had any students? Physical significance? I have given some problems. आपको दिया था. Anyway, so if you read some good books, then you will find that, as I told you, that if the value of it is negative, that means the entropy is very low, and if it is a large positive, that means the entropy is the very structured type of the things. So basically, if it is a bimolecular type of the reactions, because delta S negative, delta S positive, the measure of randomness, entropy is, the structure is not correct, because there is a scattered form, that is unimolecular reactions. But if it is a bimolecular reaction, you will get the negative values of the entropy. That means entropy is very less, that means that is very structured form. That means transition state is structural form. If you know the structure of the transition state, then you can do calculation for the vibrational motion, translational motion and rotational motion. All this it is the example of the transition state theory. Now I am giving some numerical problems. Thank you.